同学好，欢迎回到电磁理论的课程。In the next few slides, we will review the constitutive relationship. That is, the relationship between electrical and magnetic flux density and field intensity. And the material property will comes into play as permittivity and permeability. Permittivity is the 介电系数 and permeability is 介质系数, which are related to electrical dipole moments and magnetic dipole moments. They are material properties. And as you can see here, we have epsilon sub-zero and epsilon mu sub-zero. They are the permittivity and permeability of free space, which means even with nothing, even with vacuum space, a free space, you still have permittivity and the permeability. This is a little bit strange, right? I think it's strange too. But, well, this is kind of historical result. So think about that. At the time of Maxwell, I mean 1870 1870年的时候啊，在 Maxwell 那个年代 the view of the universe, okay, the basic theory of the universe is there is a substance called ether. The ether is the network, the Ethernet network. Okay, the ether is a substance that filled in the space, filled everywhere, even in vacuum space. Okay, so Maxwell equations are derived based on the basic conception, based on the basic assumption that the universe is filled with ether. So that's no wonder you have epsilon sub-zero and mu sub-zero. Okay, because, well, the space is filled with ether, so of course you have permittivity and non-zero permittivity and non-zero permeability. Okay? And unfortunately, decades later, we found that there's no so-called ether. The space, the universe is not filled with ether. It's just nothing. But when you look into the Maxwell equation, it works fine. It's still correct if you look into the result. So that's the reason why we inherit the concept of ether in the Maxwell equation. So you have non-zero permittivity and non-zero permeability for free space. Alright, so that's an interesting relationship you can have with permittivity and permeability. And the basic constitutive relationship is like that. This is something you can see in your undergraduate electromagnetic. It says that the electrical flux density is the product of permittivity and the electrical field intensity. Okay, and the magnetic flux density is the product of permeability and magnetic field intensity. Okay, but this is a kind of a simplified a result, which means if you write the relationship of electrical flux density and electrical field intensity like this, you are assuming that the material is isotropic, homogeneous, no dispersion, I mean no frequency dependence. No dispersion means no frequency dependence, no time dependence, and the flux density react instantaneously with field intensity, which means that you have once you have the field intensity, you have the flux intensity at the same time. Okay, and so that's the but in most cases, this kind of relationship is good for most materials, most material in most scenarios. For some special occasions or some very special materials or man-made material, you might have more complicated relationships. Okay, so let's look on the top left corner. The constitutive relationships, you have electrical flux density and magnetic flux density. They are functions of space and time, but they are also affected by electrical field and magnetic field. This is the more general case. Okay, so there is a possibility that the amount of electrical flux density can be affected by the amount of magnetic field intensity at that point. But the more general case is this: the electrical flux density is only related to electrical field intensity, and magnetic flux density is only related to magnetic field intensity. Based on these assumptions, we can write equation like this. So you see the electric and magnetic flux density can be written as the direct product of field intensity and the permittivity, magnetic field intensity and permeability. For free space, the permittivity epsilon sub 0 is 8.854 times 10 to the minus 12, and the permeability mu sub 0 equals to 4 pi times 10 to the minus 7. A more general form for permittivity and permeability should be written like this. This is the permittivity written in terms of frequency. So you have spatial description that's described the point you are looking into, and you also describe the frequency you are looking into. However, in general, the permittivity can be expressed as a constant. Okay, so you have no frequency dependence. You know, this is not totally correct, but it's true in general. And well, if the frequency range varies a lot, say microwave frequency range and optical frequency range, then the permittivity of a particular material may be different greatly. However, in the microwave range, in the same frequency range, say if you look at the permittivity at 3 gigahertz, 10 gigahertz, and 30 gigahertz, they may be the same. They are most likely about the same range. So it's pretty safe to say that in your interested frequency range, the permittivity and permeability can be written as a constant value. And here is another expression in writing up the permittivity relationship. It's kind of expressed in the time domain. So I can see you have a head over here, you have a spatial description, you have time description t, and you see it can be written as the product of epsilon sub 0 and a delta function, a dyadic delta function, which means it responds immediately in the time domain. Okay, so once you have electrical field, you have you have electrical flux density instantly. And because of this relationship, the constitution relationship in time domain is a little bit complicated. Let's look into the frequency domain first. The frequency domain, in the frequency domain, the electrical flux density can be viewed as the direct product of permittivity and electrical field intensity written in the frequency domain. However, if you want to look at the product in the time domain, the direct product in the frequency domain will become the convolution in the time domain. So this is related to Fourier transform, and you should be careful about this. So if you try to attempt to write the electrical flux density in the time domain, it should be in the form of convolution. So here is the convolution operator. Okay, and fortunately, in most cases, because epsilon in the time domain is the delta function, so it only exists at a specific time instant. So it can be simplified as the direct product of epsilon sub 0 and electrical field intensity description in time domain. Okay, if this is not the case, then you will end up with an integration, convolution integration in the time domain from negative infinite to positive infinite, which will be much more complicated. Okay, so the last thing we like to check on this slide is the speed of light, speed of electromagnetic wave propagation. So as you know, the speed of light equals to the inverse of the square root of the product of permittivity and permeability, which is very close to 3 times 10 to the 8th. All right. So here is a more general expression for the constitutive relationship. In linear isotropic media, that is, the relationship between electrical field intensity and electrical flux density is causal. Okay, this phrase named causal, which means the cause and the consequence. The cause and the consequence. So here you have electrical flux density as the convolution of permittivity and electrical field intensity written in the time domain. So here is the time domain convolution process, which is integral in the time domain. And it says the current value of D is a dependence of current value of D as well as past value of E. So this is a more general description. However, if epsilon exists only at a specific time instance, that is t or tau equal to 0, then the integration can be simplified as a direct product, as we seen in the previous slide, like this. Okay. So here we also review the Fourier transform relationship. This is the Fourier transform. This is the inverse Fourier transform. Okay. So the Fourier transform the function in the time domain into frequency domain, while the inverse Fourier transform change the function in frequency domain into time domain. Okay, so notice there is some difference in the Fourier transform and the inverse Fourier transform, including the exponential and the 1 over 2 pi constant. So similar relationship can be written for magnetic field. Okay, like electrical field and field intensity and electric flux density. The magnetic flux density and magnetic field intensity B and H should be written as a convolution in the time domain. And if fortunately that the permeability can be written as an instant function, as a delta function, then the expression for the relationship between magnetic flux density and magnetic field intensity can be simplified as just a direct product with a constant mu sub 0. Okay. In this set of slides, we would like to introduce the concept of magnetic charge and magnetic current, which are not seen in undergraduate electromagnetics. Why? Because they do not exist. We haven't observed actual magnetic current and actual magnetic charge. However, with the introduction of magnetic charge and magnetic current, the Maxwell equation can be more symmetric. Will look more symmetric. So for Western philosophers, they always prefer things appear in symmetric format. And as to applications, the introduction of magnetic currents and magnetic charge also helps when we try to derive relationship between E and H field in actual propagation scenarios. So that's the reason why in advanced electromagnetics we would like to add up this imaginary source, the magnetic current source and the magnetic charge source. Okay, so with the addition of magnetic current, which is usually written in terms of M, and the magnetic charge, magnetic volume charge density, which is written as rho sub mv, the Maxwell equation, in particular the Faraday's law, should be rewritten as this: the curl of E equals to the negative of time derivative of B, and the magnetic current and magnetic current density M minus Mi. I stands for impressed currents. That is the magnetic currents exercise on that point. Okay， 所以它 impressed current 指的是外力外加上去的电流，或者是外力外加上去的磁流。OK， 那像这边的安培电路定律里头嘞，后面这两项 JI 跟 JC 分别是 impressed current 跟 conduction current。所以 conduction current 是因为有外部电场，所以反映出来的电流，而 JI 指的是你强加在上面，强加在这个位置上面的电流。Okay, so as you can see, we have JI and JC. JC is the conduction current produced by the presence of electrical field and the conductivity, while JI is the impressed current, that is a current exercise on that particular point. Okay, so as you can see, with the addition of magnetic currents, the Faraday's law should be rewritten in this form. And also here is another constitutive relationship, that is the relationship between conductivity sigma and electrical field intensity and charge current density, JC. Current density is the reaction of conductivity of the material times the electrical field intensity. If you are looking into the time domain, they should appear in the convolution form. So, with the addition of magnetic current, you will also have the similar to the electrical current, you have the conservation of electrical charge, or the continuity equation. You will have the continuity equation for magnetic current as well, or conservation of magnetic charge. So you can look into, so let's check up with the conservation of electrical charge first. The divergence of J equals to the negative of time derivative of electrical charge density. So similarly, if you have magnetic current density, magnetic current, then the divergence of magnetic current shall equals to the negative of the time derivative of magnetic charge density. Okay, so magnetic charge is also related to magnetic current. Next, let's look into the modified Faraday's law, which has the magnetic current density on the right hand side. If we apply divergence operator on both sides, like this, we know the left hand side goes to 0. So the right hand side should go to 0 as well. But the right hand side will have the divergence of B and the divergence of magnetic current density. If you substitute magnetic current density, divergence of magnetic current density, then you end up with the time derivative of magnetic charge density. So therefore, with the presence of magnetic currents, the Gauss's law of magnetic field should be rewritten as well. The divergence of B is no longer 0 anymore. The divergence of B can be the magnetic charge density, rho and V. You know, this is not actually true because you don't have standalone magnetic charge. However, if we assume that the existence of magnetic charge density is true, then the Gauss's law of magnetic field should be rewritten in this form. Pretty much the same as Gauss's law of electrical charge. Next, we can utilize Stokes theory and apply this on Faraday's law. So we begin with Faraday's law in differential form. That is, the curl of E equals to the negative of time derivative of B and the magnetic current density. We apply surface integral on both sides. So we are not looking just a point. We're looking into a region enclosed with a circumference. Includes with a circumference C. So we are looking at the curve of E that goes through the surface, which is enclosed with a contour C. Then by applying the Stokes theorem, which says that the surface integral of the curve of vector A equals to the closed loop integral of that particular vector A. So we substitute the surface integral of curve E as the closed loop integral of E, and it equals to the magnetic current density flowing into the surface, because you have a minus sign here. Usually if you have a positive sign, then it refers to the magnetic currents flowing out of the surface, but here you have the negative sign, so I remark it as flow in magnetic current density, or because after the integral is flow in magnetic current. And it also related to the time derivative of flow in B. The magnetic flux density goes into the surface. So which means the two have similar significance in physics. Note that the closed loop integral of electrical field is what? Is electrical potential. It's the voltage. So the right hand side is also equivalent to voltage if you want to interpret it in terms of physics. And the Ampere's circuitial law can be rewritten as well. So if you apply surface integral on both sides, you end up with closed loop integral of magnetic field and surface integral of electrical current. So what is the physical interpretation of this? It's current, okay? And here you have time derivative of surface integral of electrical flux density. And as we have mentioned earlier, this is the so-called displacement current. So its effect is equivalent to current. Okay, so the closed loop of magnetic field, its effect is equivalent to current. All right, so similar as the result we observed in the previous slides, the closed loop integral of electrical field is voltage, and the surface integral of magnetic currents and magnetic flux density, time derivative of magnetic flux density, also equivalent to voltage, electrical potential. And in Ampere's circuitial law, we know that both sides, the physical interpretation on both sides are electrical currents. And next, let's look into Gauss's law of electrical field and Gauss's law of magnetic field. So if you turn the differential form into integral form by taking the volume integral of a small space, of a small volume, then you apply the divergence theorems, which change the closed surface integral into volume integral, and we do it inversely. So we change the volume integral into volume integral of divergence of D into closed surface integral of D. So which means, and the right hand side is charge. This means that if you have a stand-alone electrical charge, it will emit electrical field, electrical flux density, electrical flux. Okay, so as long as you have an electrical charge in the space, it will have it will provide electrical fields to its neighborhood. 所以空间中只要有电荷的存在的话，它就会有建立电场，建立电通量往外散出去，所以那一个电通量密度的封闭面积分值会不等于0，而那个封闭面积分的值就是这一个空间内部的电量电荷的总量。Okay, so similar process can be applied to magnetic field, magnetic flux density, and the magnetic charge density, and also we will have the closed surface integral of magnetic flux density must equal the amount of magnetic charge reside within the space. But of course, you know that there is no real magnetic charge. Okay, so this should be equal to 0 in reality. All right.